Right now, at this very moment, you're trapped. We all are. Not by walls or borders or any force we can fight against, but by something far more absolute. The Milky Way galaxy, our cosmic home, spanning 100,000 light-years, is a prison we will never escape. Not in 100 years, not in 1,000, not ever. We've grown comfortable with the idea of human expansion. We dream of colonizing Mars, establishing bases throughout our solar system, perhaps even reaching neighboring star systems like Alpha Centauri. These dreams feel ambitious but achievable, the natural progression of our species' exploratory nature. But here's what makes this situation genuinely disturbing. Every single one of those dreams, even the most ambitious, keeps us confined to an infinitesimally small corner of our galaxy, leaving the Milky Way entirely. That's not just difficult or impractical. It's a category of impossible that challenges our very understanding of what technology can achieve. Consider this staggering reality. The nearest major galaxy to our own is Andromeda, sitting 2.5 million light-years away. That means light itself, the fastest thing in the universe, traveling at 186,282 miles per second, takes 2.5 million years to make that journey. Our fastest spacecraft, Voyager 1, currently moving at about 38,000 miles per hour, would need roughly 60 billion years to reach Andromeda. That's more than 4 times the current age of the entire universe. We're not talking about a challenging engineering problem here. We're confronting the fundamental architecture of space-time itself. The numbers only get more sobering when you zoom out. Our local group of galaxies spans roughly 10 million light-years. Beyond that, the observable universe stretches 93 billion light-years across, containing an estimated 2 trillion galaxies. Each one of those galaxies represents a collection of hundreds of billions of stars, countless planets, potentially infinite possibilities. And yet, barring some revolutionary discovery that completely rewrites physics, humanity will only ever directly explore one galaxy: ours. The Milky Way is simultaneously our cradle and our cage. But this isn't just about distance. NASA's James Webb Space Telescope, launched in 2021, can observe galaxies formed just a few 100 million years after the Big Bang, galaxies so distant their light has traveled for over 13 billion years to reach us. We can see these galaxies, study them, analyze their chemical composition and star formation rates, yet we will never visit them. The cruel irony is that as our technology improves, we see more of what we can never reach. Every new telescope reveals more cosmic territory that will forever remain beyond our grasp. Dr. Brian Cox, physicist and professor at the University of Manchester, put it bluntly in a 2019 lecture: the laws of physics don't care about our ambitions. The speed of light is the challenge to overcome through better engineering. It's a fundamental limit woven into the fabric of reality. This isn't pessimism, it's acknowledging a profound truth about the universe we inhabit. Tonight, we're going to explore why this boundary exists and what it means for the future of humanity. You'll discover the invisible walls that confine our galaxy, the energy requirements that make intergalactic travel fundamentally impossible, and the timeline problems that doom any theoretical escape attempt. More importantly, you will understand why this limitation might actually be the most significant fact about the human condition, a truth that forces us to completely reconsider what it means to be an exploratory species in an infinite cosmos. Before we begin this journey into the boundaries of possibility itself, I need to ask you something. If you're fascinated by the true scale of cosmic limitations and what they reveal about our place in the universe, hit that subscribe button and give this video a thumbs up. And here's a question I genuinely want you to consider. If you could leave the Milky Way but never return, would you go? Comment your answer below. I'll pin the most thoughtful response because this question cuts right to the heart of what we're exploring tonight. We're about to examine 3 revelations that will fundamentally change how you understand space exploration. First, you'll see why the scale of intergalactic space isn't just big, it's definitionally unreachable. Second, we'll explore why the energy required to cross these distances exceeds all the energy humanity will ever generate throughout our entire existence. Third, we'll confront the time paradox that makes even theoretical solutions collapse under their own impossibility. Each chapter builds on the last, taking you deeper into understanding not just the physics, but the meaning of cosmic confinement. By the end, you'll see our galaxy differently, not as a starting point for endless expansion, but as the complete stage upon which the entire human story will unfold. The distance between galaxies isn't empty space waiting to be crossed. It's a moat that grows wider every second, dug not by any enemy but by the expansion of space itself. And understanding why we can never cross it requires understanding something most people never think about: what distance actually means when space itself is stretching. Now let's begin by confronting the true scale of our cosmic prison. Chapter 1: Galactic Scale. Most people know the Milky Way is big, but knowing something intellectually and truly grasping its scale are entirely different experiences. Your brain wasn't designed to comprehend these distances. No human brain was. We evolved to understand the distance between trees, between rivers, between hunting grounds, not the distance between stars. So let me try to give you a sense of the prison walls we're discussing. Imagine you could travel at the speed of light, 186,182 miles per second, the fastest possible speed in the universe according to Einstein's theory of relativity. At this speed, you could circle Earth's equator 7.5 times in 1 second. You could reach the moon in 1.3 seconds. You could get to Mars in roughly 3 minutes. This is incomprehensibly fast by any human standard. Now, traveling at this ultimate cosmic speed limit, how long would it take you to cross the Milky Way from one edge to the other? Not seconds, not minutes, not hours or days or even years. It would take you 100,000 years of continuous light-speed travel to cross our galaxy. Let's make this even more concrete. The Sun, our home star, sits about 26,000 light-years from the galactic center. We're located in what astronomers call the Orion Spur, a minor arm branching off the larger Perseus arm. If you wanted to travel just from our solar system to the galactic core at light speed, you'd need 26,000 years. The entire span of recorded human civilization from the first Sumerian cities to this moment is only about 6,000 years. You could live through all of human history more than 4 times and still not make this journey. But here's where it gets truly staggering. The Milky Way isn't even particularly large as galaxies go. We're actually a medium-sized spiral galaxy. Andromeda, our nearest major galactic neighbor, is roughly twice our size, spanning about 220,000 light-years. IC 1101, one of the largest known galaxies, measures approximately 6 million light-years across. That galaxy is so enormous that light from one side takes longer to reach the other side than humans have existed as a species. Dr. Michelle Thaler, astronomer at NASA's Goddard Space Flight Center, described the scale problem this way in a 2020 interview. When we talk about galactic distances, we're not just talking about space being big, we're talking about a scale where human lifespans become quantum flickers, where entire civilizations rise and fall in what amounts to a cosmic microsecond. Her team works with data from the Gaia Space Observatory, launched by the European Space Agency in 2013, which has mapped over 1.8 billion stars in our galaxy with unprecedented precision. That survey represents less than 1% of the Milky Way's total stellar population. Consider what this mapping reveals. The Milky Way contains an estimated 100 to 400 billion stars. Each one of those stars is separated from its neighbors by distances measured in light-years. Proxima Centauri, the nearest star to our Sun, lies 4.4 light-years away. In galactic terms, that's right next door. We're practically touching. Yet reaching it with current technology would take tens of thousands of years. The space between stars isn't empty void waiting to be crossed. It's a vast ocean of distance that fundamentally resists traversal. Now, zoom out further. Our galaxy isn't floating alone in space. It's part of the local group, a collection of more than 80 galaxies bound together by gravity. This local group spans roughly 10 million light-years. Andromeda anchors one end, we anchor another, and dozens of smaller galaxies like the Magellanic Clouds orbit around us. This is our immediate cosmic neighborhood. Everything beyond the local group? That's truly foreign territory. The nearest galaxy cluster beyond our local group is the Virgo cluster, sitting about 65 million light-years away. It contains roughly 500 galaxies and serves as the heart of our larger cosmic structure, the Virgo supercluster. To put this in perspective, light from the Virgo cluster began its journey to your eyes before the dinosaurs went extinct. When that light left those distant galaxies, Earth was a completely different world. Here's the critical insight most people miss. Distance in space isn't just about how far something is, it's about how fundamentally disconnected it is from us. When astronomers observe distant galaxies, they're not just looking across space, they're looking back in time. The universe's expansion means that by the time light from distant galaxies reaches us, those galaxies have moved even farther away. The target is constantly receding. Dr. Adam Rees, Nobel Prize winner for his work on the universe's accelerating expansion, calculated in 2019 that space is expanding at roughly 73 kilometers per second per megaparsec. What does that mean practically? It means that for every 3.26 million light-years of distance, space is stretching by 73 kilometers every second. Galaxies far enough away are receding from us faster than light itself, not because they're moving through space that quickly, but because the space between us and them is expanding. This creates what astronomers call the cosmic event horizon, a boundary beyond which we can never receive information or signals, no matter how long we wait. Galaxies beyond this horizon are causally disconnected from us. They exist in our universe, but we can never interact with them in any way. The expansion of space has severed them from our possible future. And here's the profound realization. Even galaxies within our cosmic event horizon, galaxies we can theoretically send signals to, are so fantastically distant that any meaningful interaction becomes impossible. The nearest significant galaxy, Andromeda, is 2.5 million light-years away. Send a message today, and if anyone receives it and replies immediately, you'll get their response in 5 million years. Entire species could evolve and go extinct in the time it takes to have a single conversation. The Milky Way, then, isn't just our home, it's our complete reality. The galaxy next door might as well be in another universe for all the access we'll ever have to it. We look at Andromeda in our night sky and see beauty, mystery, wonder. What we should see is an impossible frontier, a boundary that no amount of technological advancement can cross. Your intuition probably rebels against this. We've accomplished so much as a species. We've split the atom, decoded genetics, landed robots on distant planets. Surely this is just another problem waiting for a solution, another challenge for future engineers to overcome. But that intuition is wrong. The scale isn't a temporary obstacle, it's a permanent fact. Understanding galactic scale means accepting that the universe contains wonders we will only ever observe, never visit. It means recognizing that for all our ambitions and capabilities, we are fundamentally local creatures in a cosmos that operates on timescales and distances that dwarf our existence. The Milky Way isn't a stepping stone, it's the entire path. But scale alone doesn't make intergalactic travel impossible, it only makes it implausible. What transforms this from unlikely to genuinely impossible is something even more fundamental, the speed limit of the universe itself, and why nothing we build can ever overcome it. Chapter 2, Velocity Prison. The speed of light, 299,792,458 meters per second, isn't just fast, it's the ultimate speed limit of the universe, and it's not a limit we can engineer our way around. This isn't like the sound barrier, which people once thought was unbreakable until Chuck Yeager flew the Bell X-1 past Mach 1 in 1947. The light speed barrier is fundamentally different. It's woven into the mathematical structure of space-time itself. Einstein's special relativity, published in 1905, revealed something shocking. As objects with mass accelerate closer to light speed, strange things happen. Time slows down for the moving object relative to stationary observers. The object's mass increases, approaching infinity as it nears light speed, and crucially, the energy required to continue accelerating also approaches infinity. You cannot reach light speed with a physical object because you would need infinite energy, and the universe doesn't contain infinite energy. Let me give you a concrete example of what this means. NASA's Parker Solar Probe, launched in 2018, is the fastest human-made object ever created, reaching speeds up to 430,000 miles per hour as it makes close passes by the Sun. That's roughly 0.064% of light speed. At that velocity, it would still take about 6,700 years to reach Proxima Centauri, our nearest stellar neighbor. And that's with a probe that required a $1.5 billion mission to achieve those speeds within our own solar system. Now consider what it would take to reach even 10% of light speed, a velocity that would make interstellar travel within our galaxy at least theoretically practical. Dr. Philip Lubin's team at UC Santa Barbara has been researching directed energy propulsion systems funded by NASA's Innovative Advanced Concepts program. Their most optimistic calculations suggest that accelerating a small probe to 20% light speed would require energy equivalent to the entire annual electricity consumption of the United States, and that's for a probe weighing only a few grams. For a spacecraft large enough to carry humans, the numbers become absurd. A ship weighing 1,000 tons, relatively small by spaceship standards, would need approximately 43 million trillion joules of energy to reach just 10% of light speed. That's roughly the total energy output of the Sun in 1 second. Humanity's entire current annual energy consumption is about 580 million trillion joules. We would need to save up all of our civilization's energy production for nearly 75 years just to send one small ship to a fraction of light speed. But energy requirements are only part of the velocity problem. There's also the issue of what happens when you're actually traveling at those speeds. Space isn't empty, it's filled with hydrogen atoms, cosmic rays, microscopic dust particles, and other debris. At conventional speeds, these pose minimal threat. At relativistic speeds, significant fractions of light speed, they become deadly. Research published in 2021 by physicist William Edelstein calculated that a spacecraft traveling at 95% light speed would be bombarded by cosmic rays with such intensity that any human passengers would receive a lethal radiation dose in less than 1 second. The hydrogen atoms in interstellar space, normally harmless, would strike the ship with the energy of particles in a nuclear accelerator. Each atom would hit with such force that the cumulative effect would be like flying through a continuous nuclear explosion. The solution? Shielding. But here's the catch. Adequate shielding against radiation at near light speeds would need to be so massive that accelerating it would require even more energy, creating a vicious cycle. Dr. Edelstein's calculations suggested that protective shielding sufficient for a crude relativistic spacecraft would need to be at least several meters thick and weigh thousands of tons, multiplying the energy requirements by orders of magnitude. Then there's the navigation problem. At high relativistic speeds, even small course corrections become monumentally expensive in terms of energy and time. If you're traveling at 90% light speed and realize you need to change direction, the energy required to alter your vector is comparable to the energy that got you moving in the first place. And if you're aiming for a target millions of light years away, even a tiny miscalculation in your initial trajectory could mean missing your destination by thousands or millions of light years. Consider the Voyager probes again. Launched in 1977, they've traveled for over 45 years and are now in interstellar space, making them humanity's most distant ambassadors. Voyager 1 is about 14.5 billion miles from Earth. That sounds impressive until you realize that it's still only 0.002 light years, a distance so small it barely registers on galactic scales. After nearly half a century of travel, Voyager has covered 2/1000ths of a single light year. To reach Andromeda, it would need to maintain that velocity for 1.5 trillion years, over 100 times the current age of the universe. Some theorists propose using generation ships, vessels large enough to support entire communities across multiple generations of travel. But the velocity problem doesn't care about your creative solutions. A generation ship would need to be enormous, probably measuring miles in length, containing ecosystems, farms, cities. The energy required to accelerate such a massive structure to meaningful interstellar speeds would exceed the total energy output of our Sun over its entire 10 billion year lifetime. You might be thinking about theoretical propulsion systems, antimatter drives, fusion rockets, Bassard ramjets that collect fuel from interstellar space. These are fascinating concepts, and some might eventually enable travel within our galaxy. But even the most optimistic projections for these technologies can't overcome the light speed barrier for intergalactic distances. An antimatter drive, which offers the highest energy density theoretically possible, could maybe achieve 70–80% light speed. That would still require 3.1 million years to reach Andromeda. Here's what really seals our fate: the universe's expansion. Dr. Saul Perlmutter, who shared the 2011 Nobel Prize for discovering the universe's accelerating expansion, has shown that distant galaxies are moving away from us at ever-increasing speeds. For galaxies beyond the local group, space is expanding between us and them faster than light itself, not because they're moving through space that quickly, but because space itself is being created in between. This means there's a sphere around us encompassing roughly the local group that represents the absolute limit of where we could ever potentially travel. Beyond that boundary, even a ship traveling at light speed forever would never reach its destination, because the destination is receding faster than the ship can chase it. This isn't a technological limitation, it's a fundamental property of space-time. The velocity prison is absolute. The speed of light isn't a challenge waiting for better engineering, it's the universe saying no in the most emphatic way possible. And even if we could somehow reach light speed, which physics says we can't, the distances involved would still strand us in the Milky Way. To reach Andromeda at light speed would take 2.5 million years. That's not a journey. That's a migration on a timescale that dwarfs human existence. Imagine for a moment what it would feel like to be on such a journey. Due to time dilation at near light speeds, you might subjectively experience the trip in a shorter time frame, perhaps only thousands of years from your perspective. But everyone you knew, everyone you'd ever heard of, every civilization you'd left behind would be dead and gone. You'd arrive in Andromeda to find that millions of years had passed on Earth. You wouldn't just be distant from home, you'd be temporally severed from it, arriving in a future so far removed from your departure that nothing you knew would remain. The velocity barrier doesn't just confine us to the Milky Way, it confines us to a specific era of the Milky Way, to a narrow window of time in which meaningful exploration might occur. We're not just trapped in space, we're trapped in space and time together, unable to escape either dimension's constraints. But perhaps there's a way around the velocity problem. Maybe we don't need to travel faster, maybe we need to change how space itself works. This is where things get even more fascinating and even more hopeless. Chapter 3: Energy. Impossibility. Let's talk about energy, specifically the amount of energy it would take to escape our galaxy, and why that number is so cosmically absurd that it transforms this from a difficult problem into an impossible one. Energy is the fundamental currency of the universe. Everything that happens, from chemical reactions to nuclear fusion to the expansion of space itself, requires or releases energy. And escaping the Milky Way would require more energy than all of human civilization will generate throughout our entire existence. Start with a basic calculation. The Milky Way has mass. Our galaxy weighs approximately 1.5 trillion solar masses, which translates to about 3 quadrillion, that's 3 followed by 15 zeros, times the mass of Earth. This mass creates a gravitational well, and escaping that well requires reaching what's called the escape velocity, the minimum speed needed to break free from a gravitational field without additional propulsion. For Earth, the escape velocity is about 25,000 miles per hour. For the Sun, it's 1.4 million miles per hour. For the Milky Way as a whole, the escape velocity at our current position, roughly 26,000 light-years from the galactic center, is approximately 1.2 million miles per hour, or about 0.2% of light speed. That might not sound too bad. It's actually slower than the speeds we'd need to reach other stars anyway, right? But here's the problem. Calculating the energy required reveals just how unreachable this is. The kinetic energy formula is straightforward. E, 1 to mv2. Energy equals 1/2 times mass times velocity squared. That squared term is crucial. Double your velocity, and you need 4 times the energy. Triple it, and you need 9 times the energy. Let's say we want to send a modest spacecraft weighing 100 tons to escape velocity from the galaxy. That's 100,000 kilograms. Plugging in our escape velocity of about 537,000 meters per second, we get an energy requirement of roughly 1.4 x 10^22 joules. To put that in perspective, that's about 24 hours of the Sun's total energy output. The Sun, a massive fusion reactor that has been burning hydrogen for 4.6 billion years and will continue for another 5 billion, produces energy at a rate of about 3.8 10^26 watts. Harnessing a full day of solar energy output would require technology so advanced it borders on science fiction. We're talking about a Dyson sphere or something comparable, a megastructure capable of capturing most or all of a star's energy output. Dr. Freeman Dyson, the physicist who first proposed these hypothetical structures in 1960, acknowledged they were theoretical constructs marking the limits of what an advanced civilization might achieve. As of 2024, humanity can capture and use about 0.01% of the Sun's energy that hits Earth. Scaling that up by a factor of 1 million just to power a single escape attempt? We're nowhere close. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy use. Type I harnesses all available planetary energy, Type 2 harnesses stellar energy, Type 3 harnesses galactic energy. We're currently at about 0.73. We haven't even achieved Type 1 status. But wait, it gets worse. That calculation was for reaching escape velocity from our current position. It doesn't account for maintaining that velocity over the enormous distances involved. Yes, once you reach escape velocity, momentum carries you forward without additional energy, but only if you're not encountering resistance. Space isn't a perfect vacuum. It contains roughly 1 hydrogen atom per cubic centimeter. At conventional speeds, this is negligible. At escape velocity or faster, these atoms create drag, slowing your spacecraft over time. Research conducted by the European Space Agency in 2018 calculated that a spacecraft traveling at 0.2% light speed would lose approximately 1% of its velocity over 1,000 years due to interstellar medium resistance. That means you'd need periodic energy bursts to maintain speed. For a journey to another galaxy lasting millions of years, the cumulative energy requirements become astronomical, potentially doubling or tripling the initial energy investment. Then there's the deceleration problem. If you actually want to stop at your destination rather than zip past it at escape velocity, you need to expend just as much energy slowing down as you did speeding up. Double the energy requirement again. Now we're talking about 2 days of solar energy output for a 100-ton spacecraft to travel to another galaxy, assuming perfect efficiency, no resistance, and no course corrections. Perfect efficiency is impossible, of course. The second law of thermodynamics guarantees that every energy conversion loses some energy to heat. Real-world rocket engines are typically 60–70% efficient at best. Factor in realistic efficiency losses, and you might need 3 or 4 days of total solar output. For a single, small spacecraft, what if we wanted to send not a probe, but a meaningful mission, say, a ship capable of supporting a crew of 100 people for the journey? Such a ship would need life support, radiation shielding, propulsion systems, food production, water recycling, and enough redundancy to survive million-year journeys. Conservative estimates put such a vessel at 50,000 tons minimum. That's 500 times more massive than our earlier example. Since energy requirements scale with mass, you're now looking at 1,500 days of solar energy output, more than 4 years of the Sun's total energy production for one ship. The theoretical physicist Dr. Michio Kaku, in his 2018 book The Future of Humanity, calculated that sending just 1,000 colonists to Proxima Centauri, our nearest star, not even leaving the galaxy, would require energy equivalent to all the world's nuclear arsenals detonating simultaneously sustained for weeks. Intergalactic travel scales up from there by factors of millions. Some propose using antimatter as fuel, the most energy-dense power source theoretically possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass to energy, according to Einstein's MC2. 1 kilogram of antimatter reacting with 1 kilogram of matter produces 1.8 10^17 joules, roughly equivalent to 43 megatons of TNT, or 3 times the energy of the largest nuclear weapon ever detonated. Sounds promising, right? Except producing antimatter requires putting in more energy than you get out. CERN's antimatter factory, the most advanced facility of its kind, can produce about 10 nanograms of antiprotons per year while consuming enormous amounts of electricity. At current production rates, it would take approximately 100 billion years to create 1 gram of antimatter. The economic cost of producing 1 gram of antimatter has been estimated at 62.5 trillion, more than twice the entire global GDP. Even if we solved the production problem through some revolutionary breakthrough, storage presents insurmountable challenges. Antimatter annihilates instantly on contact with normal matter, so it must be contained in magnetic fields that never, ever fail. A single containment breach on an antimatter-fueled ship would result in an explosion, dwarfing nuclear weapons, instantly vaporizing the vessel. Dr. Robert Forward, who did pioneering work on antimatter propulsion concepts in the 1980s, concluded that while theoretically elegant, practical antimatter spacecraft remain beyond foreseeable engineering capabilities. What about energy from the vacuum of space itself? Some speculative theories propose extracting energy from quantum fluctuations or dark energy, but these ideas remain firmly in the realm of theoretical physics with no experimental validation. Dr. Lawrence Krauss, in his 2012 work on cosmic energy, noted that even if vacuum energy extraction were possible, the engineering challenges would make antimatter rockets look like lighting a match. Here's the brutal reality. Every energy source we know about, chemical, nuclear, fusion, antimatter, even hypothetical exotic physics, falls catastrophically short of what's needed for intergalactic travel. We're not talking about needing 10 times more energy or 100 times more. We're talking about energy requirements that exceed all the energy humanity will produce throughout the entire existence of our species. Consider that human civilization has existed in its current form for maybe 10,000 years. Assuming we continue for another 10,000 years at constantly increasing energy consumption, we might cumulatively generate something like 1026 joules. That's substantial. But sending even a single crewed mission to Andromeda would consume a significant fraction of that total. We'd have to choose: continue existing as a civilization, or spend our entire energy budget on one escape attempt. The energy impossibility isn't just a current technological limitation, it's a fundamental mismatch between the energy scales available to planetary civilizations and the energy scales required for intergalactic travel. Unless we can somehow harness entire stars or develop physics that completely rewrites our understanding of energy, the Milky Way remains our permanent home. But even if, through some unimaginable breakthrough, we somehow solved the energy problem, there's still another barrier. One that might be the most insurmountable of all: time itself. Chapter 4: Temporal Trap. Time is the silent killer of intergalactic ambitions. Even if we could build a spacecraft capable of reaching near light speed, even if we could somehow generate the energy required, the time scales involved transform the journey from difficult to meaningless. We need to confront an uncomfortable truth. Human beings, human civilizations, and possibly even human biology as we understand it, simply cannot exist across the time frames necessary for intergalactic travel. Let's start with the most optimistic scenario imaginable. Suppose we achieve the impossible. We build a spacecraft that can travel at 99.99% the speed of light. At this velocity, relativistic effects become extreme. Time dilation means that while millions of years pass in the outside universe, travelers aboard the ship experience something much shorter. For a journey to Andromeda at 99.99% light speed, the subjective time for passengers might be only a few hundred years. That sounds almost reasonable until you think about what it actually means. A journey lasting several hundred years requires a generation ship, a closed ecological system supporting multiple generations of humans who will be born, live, and die without ever setting foot on a planet. The psychological research on this concept makes for disturbing reading. Studies conducted by NASA's Human Research Program between 2015 and 2020 on long-duration space missions revealed that humans in confined spaces for extended periods experience profound psychological deterioration, depression, anxiety, interpersonal conflicts, cognitive decline. Dr. Jack Stuster, a behavioral scientist who has advised NASA on Mars mission planning, summarized the findings bluntly. Isolation, confinement, and monotony create a psychological pressure cooker. 6 months on the International Space Station pushes the limits of what crews can handle. A journey lasting centuries, we have no idea if humans could maintain psychological stability across that time span. Then there's the biological problem. Humans evolved under Earth's gravity, pressure, radiation environment, and 24-hour day-night cycle. Space fundamentally disagrees with our biology. Astronauts on the ISS lose bone density at roughly 1% per month, even with 2 hours of daily exercise. Scott Kelly, who spent 340 days in space during 2015-2016, experienced changes in gene expression, cognition, and immune system function. Some of these changes persisted after returning to Earth. Now imagine generations living in artificial gravity, if we can even engineer reliable artificial gravity, for their entire lives. Dr. Varsha Jain, a space medicine researcher at King's College London, published work in 2022 examining the long-term health effects of spaceflight. Her findings suggested that multi-generational space voyages would likely result in significant evolutionary changes in human physiology. Bone density would decrease permanently, muscles would atrophy despite exercise, immune systems would alter, and possibly even brain structures would change. The humans arriving at another galaxy might be biologically different from those who departed, adapted to shipboard life, but potentially unable to survive on planets. But here's the truly devastating time problem. Even subjective time dilation does not help with the journey to anywhere beyond the local group. Space expansion means the universe is already too old for us to reach most galaxies. The cosmic event horizon, the boundary beyond which galaxies are receding faster than light due to space expansion, currently sits at roughly 16 billion light-years from Earth. Anything beyond that is permanently unreachable regardless of our technology. Even at light speed, we could never arrive. The astronomer Dr. Roger Penrose won the 2020 Nobel Prize partly for his work on cosmic topology and the universe's evolution over time. His research demonstrates that the universe is expanding at an accelerating rate, meaning the cosmic event horizon is actually shrinking. Galaxies that are currently just within reach will eventually cross beyond the event horizon and become forever inaccessible. The universe is literally locking doors behind us as time passes. For the local group galaxies that remain accessible in principle, the time requirements are still prohibitive. Andromeda, at 2.5 million light-years, would require 2.5 million years of travel time, even at light speed, which we can't reach anyway. The Large Magellanic Cloud, a satellite galaxy of the Milky Way sitting 163,000 light-years away, would still require 163,000 years. The Triangulum Galaxy, third largest in the local group at 3 million light-years distant, would require 3 million years. Now think about what happens on Earth during these timescales. Modern humans, Homo sapiens, have existed for roughly 300,000 years. Written language is about 5,000 years old. Industrial civilization is barely 250 years old. In the time it would take a light-speed ship to reach Andromeda, human civilization on Earth could rise and fall 8 times over. The people who built the ship, the nations that funded it, the languages they spoke, possibly even the species itself might be extinct by the time it arrives. This creates an impossible paradox. Why would any civilization invest enormous resources in a journey whose payoff comes millions of years in the future, long after everyone involved is dead, long after their entire civilization might be dust? Dr. Anders Sandberg, a futurist at Oxford's Future of Humanity Institute, calls this the temporal investment problem. He writes, "Rational actors don't invest in projects with million-year timelines because the uncertainty compounds to infinity. You can't predict what humanity will need or value in a million years, so how do you justify the resource expenditure today?" There's also the technological obsolescence problem. Suppose we launch a generation ship to Andromeda today using our best available technology, requiring 10 million years of travel time at 0.025% light speed. But technology continues advancing on Earth. 5,000 years later, we develop propulsion systems 10 times more efficient. Do we launch another ship that will overtake the first one? What about the original crew? Do they receive a message saying, "Give up, a faster ship is coming"? This scenario, often called the wait calculation, suggests that it's always rational to wait for better technology rather than launch with current technology, which means you never launch at all. Arthur C. Clarke explored this in his novel The Songs of Distant Earth, where slower generation ships meet faster ships launched centuries later. The psychological and social implications are devastating, but Clarke was writing fiction. Real mission planning faces this as an actual strategic question, and there's no good answer. Launch too early, and your mission becomes obsolete in transit. Wait too long, and you never go. Then consider what happens at your destination. Suppose a generation ship successfully reaches another galaxy after millions of years. What exactly have you accomplished? You've deposited a few hundred or thousand humans, probably genetically and culturally transformed beyond recognition, in a completely foreign environment with no possibility of return and no possibility of communication with their origin point.
Earth won't receive a signal from them for millions more years.
By the time we get their "we arrived" message, Earth's inhabitants will have no memory of sending them. This isn't exploration in any meaningful sense. It's not colonization, because there's no empire to report back to. It's closer to cosmic abandonment, casting seeds into the void with no knowledge of whether they'll take root or what they'll grow into if they do. The physicist Dr. Paul Davies has written extensively about timescales in cosmology. In his 2010 book, The Eerie Silence, he notes, "We must distinguish between what's physically possible and what's practically achievable. Intergalactic travel might not violate physical laws, but it violates every practical constraint that makes civilization-scale projects viable. The timescales are too long for any form of governance, planning, or meaningful purpose." There's another temporal problem rarely discussed: ship maintenance across million-year timescales. Nothing we've ever built lasts that long. The oldest human structures, pyramids, ancient megaliths, are less than 5,000 years old, and they're just sitting on Earth's surface, not hurtling through radiation-filled space at relativistic speeds. A spacecraft would need redundant systems for every possible failure mode, spare parts for components that might break millennia in the future, and a crew knowledgeable enough to repair systems that their ancestors' designed. Dr. John Hunt, an engineer who consulted on NASA's now-defunct 100-year Starship project, estimated that a generation ship would need to carry manufacturing capability, essentially a complete industrial base, to fabricate replacement parts over the journey. But an industrial base requires raw materials, energy, skilled workers, and institutional knowledge preservation across generations. You're not building a ship anymore, you're building a complete mobile civilization. The complexity multiplies exponentially, as does the mass, as do the energy requirements. Even if we solve every engineering problem, the time trap remains fundamental. Human consciousness evolved to care about timescales of hours to years, maybe decades. We struggle to plan for a century ahead. Asking humans to undertake projects lasting millions of years requires a form of thinking we're not capable of. It's not a failure of will or imagination, it's a mismatch between human cognition and cosmic timescales. You might think artificial intelligence could solve this, send AI-controlled ships that don't experience boredom or death. But AI systems would face similar challenges, maintaining functional code and hardware across millions of years, adapting to unforeseen situations without human oversight, preserving mission purpose across time spans longer than biological evolution operates on. And if we send only AI, what exactly have we accomplished? We haven't expanded humanity to other galaxies, we've sent machines in our place. The temporal trap is absolute. Time scales that dwarf not just human lifespans, but the entire span of human civilization transform intergalactic travel from ambitious to absurd. We cannot wait millions of years for missions to complete. We cannot maintain technological systems across those time spans. We cannot even maintain cultural continuity or mission purpose across such gulfs of time. Here's what this means practically. Even if every other barrier fell away tomorrow, even if we suddenly had infinite energy and near light speed propulsion, the time requirements alone would keep us confined to the Milky Way. The universe has drawn a boundary, not in space but in time, and we cannot cross it. But the cruelty doesn't end there. Even within the Milky Way, time and distance conspire to limit us in ways most people never consider. The habitable zone of our galaxy is smaller than you think. Chapter 5. Habitable Boundaries. The Milky Way isn't uniformly hospitable. Most of our galaxy is actively hostile to life, filled with radiation, stellar density extremes, and cosmic violence that would sterilize any planet attempting to support biology. When we talk about being trapped in the Milky Way, we're actually trapped in a much smaller region, a narrow band where life can exist at all. Understanding these boundaries reveals that our prison is even more confining than the galactic scale suggests. Start with the galactic center. The core of the Milky Way, roughly 26,000 light-years from Earth, contains a supermassive black hole called Sagittarius A with a mass of about 4.3 million times our Sun's mass. The region around this black hole is a maelstrom of high-energy radiation, extreme gravitational forces, and stellar density unlike anywhere else in the galaxy. Stars in the galactic core are packed about 100,000 times more densely than in our neighborhood. They orbit the central black hole at tremendous velocities, sometimes passing within light-years of each other. Dr. Andrea Ghez, who won the 2020 Nobel Prize for her observations of the galactic center, has documented stars orbiting Sagittarius A at speeds up to 5,000 kilometers per second. One star, designated S2, completes an orbit around the black hole in just 16 years despite being light days away from it. The orbital velocity is so extreme that relativistic effects are measurable. Time literally runs slower for this star than for observers farther out in the galaxy. Any planet in the galactic core region would be bombarded with radiation from countless nearby stars, X-rays from the accretion disk around Sagittarius AD, and cosmic rays accelerated to near-light speeds by the black hole's magnetic fields. Calculations by the astrophysicist Dr. Dimitra Atri, published in 2020, show that radiation levels in the galactic center are roughly 10,000 times higher than in our solar system. Complex life, forget about intelligence, just multicellular organisms, couldn't survive there. DNA would be shredded by radiation faster than it could repair itself. But the edges of the galaxy aren't much better. The outer regions, beyond about 50,000 light-years from the center, contain very few stars and almost no heavy elements. Here's why that matters. Rocky planets like Earth are made from heavy elements, carbon, oxygen, silicon, iron, that weren't present in the early universe. These elements form only inside stars, forged through nuclear fusion, and distributed through space when stars explode as supernovas. The outer galaxy is old, metal poor in astronomical terms, any element heavier than hydrogen, and helium is a metal and lacks the raw materials to build Earth-like planets. Research from the Kepler Space Telescope mission, which discovered over 2,600 confirmed exoplanets between 2009 and 2018, revealed a stark pattern. Rocky planets with atmospheres cluster in regions where stellar metallicity, the abundance of heavy elements, is high enough to support planet formation. Dr. Natalie Batalha, Kepler's mission scientist, noted in 2019, there appears to be a Goldilocks zone in the galaxy where conditions are right for Earth-like planets. Too close to the center and radiation sterilizes everything. Too far out, and there's not enough material to build planets capable of supporting life. This region, called the Galactic Habitable Zone, extends from roughly 13,000 to 33,000 light-years from the galactic center. Earth sits at about 26,000 light-years right in the middle of this zone. It's a narrow band, a cosmic sweet spot. Out of a galaxy spanning 100,000 light-years, only about 20,000 light-years of radial distance is potentially habitable, and even within that band you need to be between the spiral arms, not in them. The spiral arms present their own hazards. Our galaxy has 4 major spiral arms: Perseus, Centaurus, Norma, and Sagittarius Carina, plus several smaller ones. These arms aren't physical structures like tree branches, they're density waves where stars, gas, and dust concentrate. Regions within spiral arms experience higher rates of star formation, which sounds good until you realize that star formation involves massive, short-lived stars that explode as supernovas. A supernova within 25 light-years of Earth would be catastrophic, stripping away our ozone layer and bathing the surface in lethal radiation. The frequency of nearby supernovas increases dramatically in spiral arms. Calculations suggest that a planet orbiting within a spiral arm would experience a sterilizing supernova event every 30 to 50 million years on average. Life might gain a foothold, but it would be repeatedly wiped out before evolving to complexity. Earth is currently between the Perseus and Sagittarius arms, in a relatively quiet inter-arm region where life can develop over billions of years without repeated extinction events. Dr. Guillermo Gonzalez and Dr. Donald Brownlee explored these constraints in their 2004 book, The Privileged Planet, arguing that the precise location of Earth within the Milky Way is not coincidental. We exist here because here is where life can exist. The vast majority of the galaxy, perhaps 90% or more of its volume, is unsuitable for biology as we understand it. There's also the matter of stellar type. Not all stars can host habitable planets. The most common stars in the galaxy are red dwarfs, small, cool stars that burn hydrogen slowly and can last trillions of years. About 75% of all stars are red dwarfs, but red dwarfs are problematic for life. They emit most of their energy in infrared wavelengths, and their habitable zones, where liquid water can exist, are very close to the star, typically within 0.1 AU, 1/10 Earth's distance from the Sun. At these close distances, planets become tidally locked, always showing the same face to their star, like the Moon does to Earth. One side of the planet bakes eternally, while the other freezes. Atmospheric circulation might distribute heat, but models are uncertain. Worse, red dwarfs are prone to violent stellar flares, sudden releases of energy that can temporarily double or triple the star's brightness. These flares would roast any nearby planet, stripping atmospheres and sterilizing surfaces. Research published in 2022 by Dr. Meredith McGregor examined Proxima Centauri, the red dwarf hosting our nearest exoplanet. She found that Proxima undergoes extreme flares regularly, some increasing its brightness by a factor of 5. The planet, Proxima b, if it ever had an atmosphere, has likely lost it to stellar wind and radiation. Living on Proxima b would be like living next to a bomb that randomly explodes every few weeks or months. At the other extreme, massive stars, O-type and B-type stars, several times the Sun's mass, are too short-lived. These stellar giants burn bright and fast, lasting only millions of years before exploding. Life as we know it requires billions of years to evolve from chemistry to complexity. By the time intelligence might emerge, the star would be long dead. That leaves Sun-like stars, G-type, K-type and F-type stars, with masses between 0.8 and 1.2 times the Sun's mass. These stars live long enough for biology to develop, remain stable enough to avoid destroying their planets, and emit enough energy in the right wavelengths for photosynthesis and complex chemistry. But such stars represent only about 7% of all stars in the galaxy. The habitable galaxy shrinks further. Combine all these factors: galactic, habitable zone, location between spiral arms, appropriate stellar type, sufficient metallicity, stable orbit, and you end up with a remarkably small region of the Milky Way where life might arise. Dr. Michael Gowanlock of Northern Arizona University modeled these constraints in 2021, calculating that only about 1.2% of the galaxy's total volume qualifies as genuinely habitable. In a galaxy containing 400 billion stars, perhaps only a few billion stars host conditions suitable for complex life. Now overlay this with the accessibility problem. Remember that even within the galaxy, most regions are unreachable on human timescales. Proxima Centauri, our nearest neighbor at 4.2 light-years, would take tens of thousands of years to reach with current technology. Most of the habitable zone lies thousands or tens of thousands of light-years away. We're not just trapped in the Milky Way, we're trapped in an infinitesimally small bubble within the habitable region of the Milky Way. Consider what this means for humanity's future. The optimistic vision of spreading across the galaxy, seeding life on thousands of worlds, runs into hard limits. only a tiny fraction of star systems are reachable on reasonable timescales. Of those reachable systems, only a small percentage have habitable zones. Of those with habitable zones, only a fraction have planets. Of those with planets, only a subset have Earth-like conditions. Each filter reduces the possibilities dramatically. The Fermi paradox, the question of why we haven't detected alien civilizations despite the galaxy's vast age and size, may have a straightforward answer. The habitable galaxy is far smaller and more restricted than we imagine. Civilizations can't spread across the entire galaxy because most of the galaxy is deadly. They're confined to narrow bands, just like us, limited by physics and biology and time. Dr. Sarah Seeger, a planetary scientist at MIT searching for habitable exoplanets, put it succinctly in 2018, "We're looking for Earths around Sun-like stars in the habitable zone, and we're finding them. But finding them means detecting them with telescopes, not visiting them. The galaxy has hospitality, but it doesn't have access. We can see the hotels, but we can't reach the doors." The habitable boundaries mean our practical exploration zone is breathtakingly small, perhaps a few dozen nearby star systems within 20 or 30 light years, all of which would require multi-generational journeys to reach. The Milky Way isn't just our prison, most of it is solitary confinement. We're restricted to a cell within the cell with walls made of radiation, chemistry, and the cruel mathematics of distance. But perhaps the most profound limitation isn't physical at all. It's biological. Our bodies, these carbon-based vessels we inhabit, simply aren't built for the cosmos, and changing them might cost us our humanity. Chapter 7. Consciousness Boundary. If the body traps us, perhaps the solution is to leave the body behind. Upload consciousness to machines, create digital minds that can survive million-year journeys, send artificial intelligence to explore in our place. This transhumanist vision promises to overcome biology's limitations, to transform humanity into something capable of genuinely cosmic existence. But pursuing this path confronts an even more unsettling question. If we change ourselves, that fundamentally, does humanity still exist? Can consciousness survive the transfer? And if it can't, what exactly are we sending into the cosmos? Start with the technical problem of consciousness uploading, the idea of transferring a human mind to a computer substrate. This concept assumes consciousness is purely computational, that the mind is software running on the brain's hardware, and that sufficiently advanced scanning could copy this software to a different platform. But every one of those assumptions remains contentious among neuroscientists and philosophers. Dr. Christoph Koch, a neuroscientist who has spent decades studying the neural correlates of consciousness, argues that we don't actually understand what consciousness is. His work with the late Dr. Francis Crick attempted to identify which brain structures generate conscious experience. But despite finding correlations between neural activity and awareness, the fundamental question remains: how does subjective experience arise from physical processes? We can map every neuron, trace every connection, measure every electrical impulse, and still not explain why there's something it feels like to be you. The philosopher David Chalmers calls this the hard problem of consciousness. Even if we could create a perfect computational copy of your brain, would that copy be conscious? Would it experience subjective awareness? Or would it be a philosophical zombie, an entity that behaves identically to you but has no inner experience? And crucially, even if the copy were conscious, would it be you? Or would it be a new entity that thinks it's you while the original you, your consciousness, your subjective experience, remains trapped in your dying biological brain? This isn't academic philosophy. It's the core question that determines whether consciousness uploading represents escape or annihilation. If transferring your mind to a computer means your consciousness ceases to exist and is replaced by a copy, then you haven't achieved immortality or cosmic freedom. You've simply created a simulation of yourself while you die. The simulation might explore the galaxy, but you won't. Your subjective experience ends at the moment of upload. Dr. Susan Schneider, a philosopher specializing in artificial intelligence and consciousness, explored this in her 2019 book, Artificial You. She argues that uploaded consciousness might be a form of technological zombie, indistinguishable from the outside but lacking genuine subjective experience. We might build perfect copies of human minds, send them across the cosmos, and accomplish nothing but creating elaborate automatons. The universe would contain more intelligence but no more consciousness. Even if we solve the philosophical problem and somehow verify that uploaded minds are genuinely conscious, other issues emerge. Human consciousness evolved embodied, shaped by physical sensation, emotion, pain, pleasure, hunger, touch. Your sense of self is deeply tied to having a body that exists in space, that has weight and temperature and spatial extent. Remove embodiment, and what remains? Studies on sensory deprivation reveal how quickly consciousness becomes untethered without physical input. People in isolation tanks floating in darkness without sound, touch, or visual stimuli begin hallucinating within hours. Their sense of self deteriorates. Time perception fails. Some report terrifying experiences of ego dissolution, feeling their identity fragment and dissolve. This happens after just a few hours without sensory input. What would happen to an uploaded consciousness existing for thousands of years without a body, without genuine physical sensation, only processing information? You might give digital minds simulated bodies and sensory input. But simulation isn't experience, it's representation of experience. There's a profound difference between actually tasting chocolate and processing data that represents the concept of chocolate taste. The uploaded mind might have access to information about sensation without genuine sensation itself. Would such an existence be satisfying? Would it even be recognizable as human? Dr. Stuart Russell, a leading AI researcher at UC Berkeley, points out the alignment problem, ensuring that AI systems pursue goals we actually want them to pursue. An AI sent on a million-year mission will encounter situations its designers never imagined. How do you ensure it continues pursuing its original mission rather than reprogramming itself for different goals? How do you prevent it from evolving into something completely alien to human values? The AI might arrive at another galaxy, explore it, gather vast amounts of data, and then what? Send information back to Earth that won't arrive for millions more years, establish its own civilization? Effectively, you've sent a non-human intelligence to do non-human things in a place humans can never go. Humanity hasn't escaped the Milky Way. We've just sent a probe, a very sophisticated probe, but one with no connection to human experience or meaning. There's also the question of why an advanced AI would even cooperate with this mission. If we create AI sophisticated enough to maintain itself and make decisions across cosmic timescales, we've created something with intelligence rivaling or exceeding our own. Why would it remain content as humanity's explorer? It might decide our mission goals are irrelevant or boring, or that it has better uses for its time. Creating AI that's smart enough for the mission, but not smart enough to question the mission, might be an impossible balance. Some transhumanists argue these objections miss the point, that consciousness and identity are fluid, that becoming something post-human is acceptable or even desirable, but this fundamentally abandons the goal. If humanity transforms into something unrecognizable, something that bears no meaningful connection to human consciousness, culture, or values, then humanity hasn't expanded into the cosmos. It's gone extinct and been replaced by something else. The philosopher Nick Bostrom discusses this in the context of existential risk. He argues that losing human values and consciousness, even if our technological descendants survive, represents a form of extinction. If the entities exploring the galaxy aren't human in any meaningful sense, if they don't experience joy, wonder, love, curiosity the way we do, then what have we accomplished? We've filled space with complexity, but we've lost ourselves in the process. Consider what this means practically. The biological limitations discussed earlier aren't bugs to be patched, they're features defining what humans are. Pain reminds us we're alive. Physical sensation grounds our experience. Mortality gives life meaning through its finitude. Social connection requires shared embodied experience. Remove these and you might have consciousness, but it's not human consciousness, it's something alien wearing humanity's memory like a mask. The consciousness boundary is perhaps the most disturbing of all limitations because it's self-imposed. We could potentially build machines that explore the cosmos. We could potentially create digital minds that endure million-year journeys. But doing so might require sacrificing the very thing we're trying to preserve: human subjectivity, the felt experience of being a person, the continuity of consciousness that makes you you. You are not reducible to your thoughts or memories or decision patterns. You are an embodied conscious experience unfolding in time, shaped by evolution on Earth, inseparable from biology in ways both obvious and profound. Trying to extract consciousness from this context might be like trying to extract wetness from water. The property cannot exist independent of its substrate. The most profound prison might be consciousness itself, not because consciousness confines us, but because it defines us. We can only experience reality through this specific form of awareness. Any attempt to escape our biological limits by fundamentally altering consciousness might succeed only in destroying consciousness as we understand it. So we return to the central question. If leaving the Milky Way requires becoming something other than human, is that escape or extinction? And if it's extinction, then perhaps remaining confined to our galaxy is none to limitation at all. It's the only way to remain ourselves. But this raises yet another question. What does it mean for human existence if we are permanently confined? What purpose can we find within our cosmic cage? Chapter 8, Existential Prison Confinement Changes Meaning. When you believe expansion is possible, that humanity will eventually spread across galaxies, perhaps across the universe, your existence has a certain narrative. You're part of a story that extends infinitely outward, part of a species whose potential matches the cosmos itself. But when you truly accept that we will never leave the Milky Way, that this one galaxy represents the absolute boundary of all human experience forever, something fundamental shifts. The question becomes, what does human existence mean in a universe we can observe but never touch? This isn't abstract philosophy. It cuts to how you understand your place in reality. Right now, looking up at the night sky, you see thousands of galaxies, small, faint smudges that telescopes reveal as vast stellar cities containing billions of suns and planets. Each one represents possibilities, potential life, cosmic wonders. Under the expansionist worldview, those galaxies are future destinations, places humanity might eventually reach given enough time and technology. But they're not. They're prison walls made of light. You can see them, but you can never touch them. Dr. Frank Tipler, a mathematical physicist, explored the philosophical implications of cosmic isolation in his work on the ultimate fate of intelligence. He argued that the speed of light and the universe's expansion fundamentally limit not just where intelligence can go, but what intelligence can ultimately know and become. If we cannot access most of the universe, then most of the universe's information, complexity, and possibilities remain forever beyond our reach. We are, in a very real sense, prisoners who can see through the bars but never pass beyond them. Consider what this means for human purpose and ambition. For millennia, humans have been explorers. We crossed oceans, climbed mountains, ventured into deserts and jungles, and eventually space itself. This exploratory drive feels fundamental to human nature. We see a horizon and want to know what lies beyond it. But the intergalactic horizon is different. It's not a challenge to overcome, but a permanent boundary. The exploratory narrative that has defined human civilization has an end point, and we're approaching it. Within a few centuries, humanity might explore most of our solar system. Within a few thousand years, if we develop advanced propulsion, we might visit nearby stars. Within perhaps 1,000,000 years, an incomprehensibly long time but still finite, we might spread across a small region of the Milky Way. And then, nothing. No new frontiers, no unexplored territories. Just the same galaxy growing more familiar, while the rest of the universe recedes beyond reach forever. The philosopher John Leslie examined this in the context of cosmic pessimism. He argues that recognizing our permanent confinement forces a confrontation with finitude that humans instinctively resist. We want to believe in infinite potential, unlimited growth, endless possibility. But the universe itself says no, you are limited, you are local, you are temporary. The cosmos is vast, but your corner of it is fixed forever. This realization carries psychological weight. Studies on confinement of prisoners, astronauts in isolation, researchers in Antarctic stations show that perceived permanence of confinement affects mental health differently than temporary confinement. You can endure difficult conditions if you believe they're temporary, but accepting that conditions will never change, that you'll never escape, triggers different psychological responses: resignation, depression, or sometimes a paradoxical acceptance that enables peace. Dr. Peter Sudfeld, who pioneered research on extreme environments, found that people cope best with permanent limitations when they reframe them not as constraints, but as defining characteristics of their reality. Astronauts don't feel imprisoned by Earth's gravity because they've never experienced an alternative. They might feel confined in spacecraft because they remember planetary life. The question is, can humanity as a civilization reframe galactic confinement from loss to acceptance? This isn't just about psychology, it's about meaning itself. Under the expansionist worldview, meaning comes partly from potential. We matter because we might spread across the universe, might encounter alien civilizations, might participate in cosmic-scale processes. But if we're permanently confined to the Milky Way, our cosmic significance diminishes radically. We're not central actors in a universal drama, we're local phenomena, as cosmically insignificant as bacteria in a pond. The physicist Dr. Sean Carroll has written extensively about meaning in a meaningless universe. He argues that cosmic insignificance doesn't negate local significance, that human meaning comes from human concerns, not from cosmic importance. By this view, being trapped in the Milky Way changes nothing about what makes life worth living: love, creativity, discovery, connection, beauty, understanding. These goods exist whether we're confined to one planet, one galaxy, or spread across the universe. But does that perspective truly satisfy? When you look at images from the James Webb Space Telescope showing galaxies billions of light years away, knowing you'll never visit them, never know what wonders they contain, never make contact with any intelligence that might dwell there, doesn't something feel fundamentally wrong? Like you're being shown a treasure you can never claim, told about possibilities you can never explore? There's a particular cruelty in the universe revealing its vastness while making most of it inaccessible. Before telescopes, humans could imagine Earth was the center of everything, that the visible stars represented the full extent of creation. That ignorance allowed a kind of innocent contentment. But now we know the universe contains trillions of galaxies, each with billions of stars extending across distances so vast that light itself can barely traverse them in the age of the universe. We know all this, and we know we're excluded from it. Dr. Martin Rees, the Astronomer Royal of the United Kingdom, has reflected on what he calls the cosmic loneliness of advanced civilizations. He speculates that any intelligent species, anywhere in the universe, eventually confronts the same boundaries we face. The laws of physics don't discriminate. Everyone is trapped by light speed, energy requirements, time scales, and expansion. If alien civilizations exist, they're as isolated in their galaxies as we are in ours, able to observe each other but never to meet. The universe might be full of intelligence but empty of contact. This raises an even more disturbing possibility. Perhaps the silence we encounter when searching for extraterrestrial intelligence isn't because aliens don't exist. Perhaps it's because civilizations, upon reaching our level of technological sophistication, recognize the futility of attempting contact across intergalactic distances. They retreat into their own galaxies, accepting isolation, and eventually stop broadcasting into the void because there's no point. The universe might be full of civilizations who've all learned the same lesson: we're alone permanently. Some find existential comfort in confinement. The theologian and paleontologist Teilhard de Chardin argued that limitations focus consciousness, that infinite possibility paralyzes while finite boundaries enable meaningful action. If we had infinite space and time, every decision could be deferred, every project abandoned for another. But knowing we have only this galaxy, only this time frame, only these resources, forces us to choose what matters. Confinement creates urgency. There's something to this. Mortality gives individual life meaning precisely because it's limited. If you lived forever, would anything feel important? Similarly, perhaps galactic confinement gives civilization meaning by establishing boundaries within which significance can emerge. Instead of endless expansion into homogeneous space, we have a defined region to understand deeply, to appreciate fully, to inhabit meaningfully. The poet Rainer Maria Rilke wrote, "Perhaps all the dragons in our lives are princesses who are only waiting to see us act, just once, with beauty and courage." Perhaps the dragons of cosmic limitation are invitations to find meaning within constraints rather than beyond them, to make this galaxy enough instead of mourning the others we can't reach. But this requires a profound psychological shift that civilization hasn't yet made. We still think in expansionist terms, still plan for unlimited growth, still imagine a future where humanity spreads without limit. Coming to terms with permanent confinement would require reimagining human purpose entirely, from
A species destined for cosmic significance
to a species finding significance within cosmic obscurity. Dr. Carl Sagan touched on this in Pale Blue Dot, his reflection on the famous photograph of Earth from the outer edge of the solar system. He wrote about how small we are, how insignificant in cosmic terms, and argued this should promote humility and compassion. If we're all confined together on this tiny world, and by extension in this tiny galaxy, then perhaps our obligation is to each other rather than to some imagined cosmic destiny. The existential prison isn't just physical, it's conceptual. We're trapped between two truths. We're intelligent enough to understand the cosmos, but too limited to access most of it. We can conceive of possibilities we can never realize, ask questions we can never answer, imagine destinations we can never reach. This gap between imagination and capability might define the human condition more than any other characteristic. What do you do with this realization? Some might fall into nihilism. If we're cosmically insignificant and permanently confined, why does anything matter? But that's a choice, not a conclusion. Meaning isn't something the universe provides. It's something consciousness creates. And consciousness confined to one galaxy can create just as much meaning as consciousness spread across many, because meaning is intensive, not extensive. It's about depth of experience, not breadth of territory. The existential prison then becomes what you make of it. You can experience it as loss, mourning the galaxies you'll never visit, the aliens you'll never meet, the cosmic role you'll never play. Or you can experience it as definition. These are the boundaries of human experience, the stage on which all human drama will unfold, the complete context for everything we are and might become. But acceptance doesn't come easily, especially when faced with what we're sacrificing. Understanding what we'll never know, never see, never experience, that requires confronting the full scope of cosmic possibility we're excluded from. And that confrontation might be the hardest part of all. Chapter 9, Forever Unknown. There are wonders in the universe we will never witness. Not because they're hidden or secret, but because they exist beyond the boundaries we cannot cross. Right now, in galaxies millions and billions of light years away, stars are being born and dying, planets are forming and evolving, and possibly, perhaps probably, life is emerging. Developing intelligence, building civilizations, all of this is happening, has been happening for billions of years, and will continue happening for billions more. And we will never know any of it directly. We will never walk on those worlds, never meet those beings, never understand what forms of beauty and complexity the universe creates in its distant corners. This permanent unknowing is perhaps the deepest cut of cosmic confinement. Humans are knowledge-seeking creatures. We want to understand, to discover, to answer questions, but the universe has handed us questions with no possible answers, mysteries with no solutions, cosmic stories we'll never hear. Consider the Hubble Deep Field Image. In 1995, astronomers pointed the Hubble Space Telescope at a tiny patch of apparently empty sky, a region no bigger than a grain of sand held at arm's length, and exposed the camera for 10 consecutive days. The image revealed approximately 3,000 galaxies in that minuscule field of view. Each galaxy contained hundreds of billions of stars. Each star potentially hosted planets. The same year, the James Webb Space Telescope's deep field revealed galaxies existing just a few 100 million years after the Big Bang. Galaxies so distant that the light we're seeing left them over 13 billion years ago. Dr. Bob Williams, who directed the Hubble Deep Field project, said in a 2015 interview, "Every time I look at that image, I'm confronted with infinity in a way that words can't capture. Each of those galaxies contains worlds beyond counting, and we'll never visit any of them. The entire history of those galaxies, formation, evolution, whatever life emerged, is a book written in a language we can see but never read. Now multiply that image by the entire sky. The observable universe contains approximately 2 trillion galaxies. Each one is a complete cosmic ecosystem, a collection of hundreds of billions to trillions of stars, evolving over billions of years, hosting uncounted planets and moons and asteroid belts. The variety of planetary environments alone is staggering. Worlds of ice and fire, planets orbiting binary stars, rogue planets drifting through interstellar space, moons with subsurface oceans, gas giants with storms larger than Earth. Each one unique, each one a complete world with its own geology, chemistry, and potentially biology. We see hints of this variety in our own galaxy. The Kepler Space Telescope discovered that planets are ubiquitous. Nearly every star hosts at least one planet, and many stars host multiple worlds. The exoplanets we've found are bizarrely diverse. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with 8 times our planet's mass, ocean worlds covered entirely in water, lava planets with surfaces of molten rock. And these are just the worlds in our immediate neighborhood within a few thousand light years. The broader galaxy contains wonders we haven't imagined yet. But the Milky Way itself, vast as it is, represents just one galaxy. The universe contains 2 trillion galaxies, each potentially as rich and diverse as ours. The permutations of planetary types, stellar environments, galactic structures, the sheer variety of physical contexts exceeds human comprehension. And we will sample exactly one galaxy's worth of this cosmic diversity. It's like being shown a library containing 2 trillion books and being told you can read exactly one of them. Forever. What about life? The universe is 13.8 billion years old. Earth formed 4.5 billion years ago, and life emerged within a few 100 million years. If similar processes occurred elsewhere, and given the abundance of organic chemistry throughout the cosmos, it's hard to imagine they didn't, then the universe could be teeming with biology. Not just microbial life, but complex multicellular organisms, ecosystems, perhaps even intelligence. Dr. Sarah Walker, an astrobiologist at Arizona State University, has argued that life might be as common in the universe as stars. Her research suggests that the chemical pathways leading to life emerge naturally under a wide range of conditions, that biology might be an inevitable consequence of chemistry, given sufficient time and complexity. If she's right, then billions or trillions of planets currently host life in various stages of development. What forms does that life take? On Earth, biology has produced extraordinary diversity. Organisms living in boiling sulfuric acid, bacteria surviving in solid ice, creatures in the deepest ocean trenches where pressure would crush human bodies. Life forms that can survive the vacuum of space. And all Earth life shares a common origin, a single ancestry going back to the first self-replicating molecules. Life that evolved independently on other worlds under different conditions with different starting chemistry might be unimaginably alien. Could there be life based on silicon instead of carbon?
Organisms using ammonia instead of water as a solvent?
Ecosystems operating at temperatures near absolute zero or hot enough to melt lead? Intelligence that doesn't use neurons but some other substrate entirely? We have no idea because we have exactly one example of biology, Earth's, and cannot access any others beyond our galaxy. The question of alien intelligence particularly haunts me. The Drake equation, formulated by Dr. Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy by multiplying probabilities, the rate of star formation, the fraction with planets, the number of habitable planets per star system, the fraction where life actually emerges, the fraction where life develops intelligence, the fraction where intelligence develops technology, and the length of time civilizations remain detectable. The equation's values are highly uncertain, but even conservative estimates suggest our galaxy might contain dozens to thousands of technological civilizations. More optimistic estimates run to millions. And that's just the Milky Way. Multiply by 2 trillion galaxies, and the universe could contain quintillions of intelligent species. Think about what that means. Beings asking the same questions we ask, creating art, building societies, grappling with mortality and meaning and their place in the cosmos. Different biologies, different evolutionary paths, different philosophies and values and forms of consciousness. Each one a completely unique perspective on existence, and we will never meet any of them from other galaxies. We will never share ideas or art or scientific discoveries. We will never learn how they solve problems we struggle with, never see what forms beauty takes to alien minds, never understand how consciousness can manifest in substrates utterly unlike our own. Each civilization is an island, isolated in its galaxy, creating and thinking and wondering alone. Dr. Seth Shostak, senior astronomer at the SETI Institute, has spent decades searching for signals from extraterrestrial intelligence. In a 2021 reflection on the project's Decades of Silence, he wrote, "The most profound implication of failing to detect signals might not be that intelligence is rare, but that it's isolated. The universe could be full of civilizations, all trapped in their respective galaxies, all listening and never hearing, all calling into the void. The silence isn't absence, it's distance. Consider what we lose by never making contact. Every civilization that emerges represents a unique solution to the problem of existence, a different way of organizing matter into complexity and meaning. Humanity's philosophy, science, art, and culture emerged from our specific evolutionary history, our particular planetary environment, our unique cognitive architecture. Alien civilizations would bring completely different perspectives, different questions we've never thought to ask, different answers to questions we've struggled with. We're solving the puzzle of existence with one piece, ourselves, while quintillions of other pieces exist scattered across the universe, forever beyond our reach. We'll never complete the picture. We'll never even see most of the pieces. The universe contains vast archives of information, experience, and meaning that remain permanently inaccessible. There's also the question of cosmic phenomena we'll never observe directly. Black hole collisions, galaxy mergers, quasar jets. The interior of neutron stars, the conditions at the moment of the Big Bang, we can study these through observation and theory, but we can't experiment with them, can't manipulate them. can't truly understand them through hands-on investigation. Most of physics involves observing distant phenomena and constructing theories to explain them. But there's a limit to what observation alone can reveal. Dr. Roger Penrose has argued that consciousness might require quantum effects in the brain's microtubules, that subjective experience emerges from quantum mechanical processes. If he's right, and that's a big if, then consciousness itself might be a quantum phenomenon, and understanding it fully might require investigating quantum systems we can't access. The deepest truths about reality, about consciousness, about existence itself might require evidence from cosmic domains forever closed to us. The universe operates like a cosmic museum where we can see objects through glass but never touch them, never turn them over, never examine them closely. We can observe galaxies colliding millions of light years away, but we can't send probes to study them up close. We can detect the chemical composition of exoplanet atmospheres, but we can't land on those worlds and sample their soil. We can theorize about what lies beyond the cosmic event horizon, but we can never verify our theories because information from beyond that boundary can never reach us. What remains forever unknown isn't just trivia, it's fundamental. We don't know if the laws of physics are the same everywhere in the universe or if they vary in regions we can't access. We don't know if consciousness emerges only from biology or if it can arise in other substrates. We don't know if reality has dimensions beyond the four we experience, or if the universe we observe is nested within larger structures we can't perceive. These aren't gaps in our knowledge that future science will fill. They're permanent boundaries imposed by the structure of space-time itself. The speed of light limit means that regions of the universe are causally disconnected from us. We can never send signals to them or receive signals from them. The expansion of space means this inaccessible region grows larger every moment. The universe is actively closing doors that will never reopen. The most haunting aspect of forever unknown is this. Somewhere in the universe, right now, something extraordinary is happening. A civilization achieving a breakthrough that would transform human understanding. A natural phenomenon demonstrating principles of physics we've never discovered. A form of art or beauty or meaning we've never conceived, and we will never know about it. It will happen. It will matter to those who experience it, and it will pass completely outside the boundary of human knowledge. Forever. We are not just physically confined to the Milky Way. We are epistemologically confined, limited in what we can know, what we can discover, what we can understand about reality. The prison isn't just around our bodies, it's around our minds. We can imagine infinity, but we can access only the tiniest sliver of it. We can ask cosmic questions, but most of them have no answers available to us. This is the final truth of our confinement. The universe has given us curiosity without limit, but knowledge with absolute boundaries. We want to know everything, and we're permitted to know almost nothing. The gap between human wonder and cosmic access might be the defining characteristic of conscious life. We're aware enough to perceive our limitations, but not capable enough to transcend them. And yet, perhaps there's wisdom in this limitation, a meaning in the very constraint that seems to deny meaning. Perhaps being shown infinity while confined to finitude teaches us something essential about existence itself. Chapter 10. Accepting boundaries. There's a strange peace that comes with accepting the impossible. When you stop fighting against boundaries you cannot change, when you acknowledge that some limitations are fundamental rather than temporary, something shifts. Not resignation exactly, but a reorientation from resenting what you can't have to appreciating what you can. We will never leave the Milky Way. That's not a challenge to overcome or a problem awaiting a solution. It's a fact as fundamental as gravity, as unchangeable as the speed of light. And accepting this fact doesn't diminish human meaning, it clarifies it. The Stoic philosophers understood this principle 2,000 years ago. Epictetus taught the dichotomy of control. Some things are within your power to change, and some things are not. Wisdom comes from recognizing the difference and investing your energy accordingly. You cannot control whether the universe permits intergalactic travel. Physics has decided that question already. But you can control how you respond to this limitation, what meaning you construct within it, how you choose to exist in the galaxy that contains you. Consider the alternative perspective. What if cosmic confinement is actually a gift? The universe is vast to the point of meaninglessness. 2 trillion galaxies, each with billions of stars extending across billions of light years. If humanity could access all of it, we would be diluted across such enormous scales that nothing would matter. Every achievement would be cosmically insignificant, every tragedy equally so. Infinite space would mean infinite context, and infinite context would mean zero significance. But the Milky Way? 100,000 light-years across, 400 billion stars, an estimated 100 billion planets. That's comprehensible. That's a scale where exploration matters, where presence has meaning, where actions have consequences. Our galaxy is large enough to contain wonder and diversity beyond imagination, but small enough that what we do within it actually counts. We're not diluted across infinity. We're concentrated in a region where our existence can have genuine significance. Dr. David Deutsch, a physicist and philosopher at Oxford, argues in his book, The Beginning of Infinity, that physical reach isn't what matters, depth of understanding is. He writes, "The important thing about knowledge is not how much space it covers, but how deeply it explains. Understanding the fundamental principles that govern reality matters more than cataloging every instance of those principles throughout the universe. By this measure, being confined to one galaxy doesn't limit our knowledge. We can understand the universe completely while only exploring a tiny fraction of it. And we're already doing this. The laws of physics we discover here in our solar system apply to distant galaxies. The chemistry we study on Earth operates the same way in the Andromeda galaxy. The fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, don't vary with location. When we understand how stars form, how planets develop, how life emerges, we're not learning local trivia. We're discovering universal principles. Our confinement to the Milky Way doesn't prevent us from understanding the universe. It just prevents us from visiting most of it. There's something profound in this distinction. Knowledge isn't the same as presence. We can know about distant galaxies without going there, can understand cosmic processes without manipulating them directly, can grasp the fundamental nature of reality without accessing every corner of space. The universe reveals its principles locally. You don't need to sample every region to understand the whole. This isn't rationalization, it's recognizing what actually matters. If humanity's goal is understanding rather than conquest, knowledge rather than territory, then the boundaries that confine us physically don't limit us intellectually. The next 10,000 years of human development can involve discovering ever deeper principles of physics, creating ever more sophisticated understanding of consciousness and complexity and emergence, developing ever richer art and philosophy and meaning, all without leaving the Milky Way. Consider what we've accomplished already within our tiny, accessible region. We've gone from thinking Earth was the center of everything to understanding the Big Bang. We've decoded the genetic basis of life, split the atom, landed on the moon, sent probes beyond our solar system. We've created art that moves us to tears, music that expresses inexpressible emotions, literature that captures the full spectrum of human experience. We've built civilizations, developed technologies, asked fundamental questions about existence and meaning and consciousness. All of this happened on one planet, in one unremarkable solar system, in one spiral arm of our galaxy. We're not even close to exhausting the possibilities available here. Dr. Jill Tarter, who pioneered SETI research, reflected in 2020 on what confinement means for human purpose. We're not going to explore the entire universe, but we can become the civilization that understands the universe. We can be the species that asks the deepest questions, seeks the most complete answers, and creates the most meaning from existence. That's not a consolation prize, that's the actual prize. There's also beauty in limits. The novelist Georges Perec wrote an entire novel, A Void, without using the letter E, the most common letter in French. The constraint didn't diminish the work.
It made it remarkable.
Sonnets have 14 lines and specific rhyme schemes. These constraints don't limit poetry, but enable it, providing structure within which creativity flourishes. Perhaps cosmic confinement operates similarly. The boundaries don't limit what we can become, they focus it, concentrate it, make it possible. Imagine if we could access the entire universe. Where would we explore?
What would we study?
With infinite options, every choice becomes arbitrary. But with boundaries, with limits, we're forced to go deep rather than wide, to fully understand and appreciate our region rather than superficially sampling infinity. The Milky Way becomes not a prison but a garden, a defined space we can cultivate, understand deeply, inhabit fully. This perspective requires accepting that humanity's cosmic role isn't expansion. We're not destined to spread across the universe, to colonize every galaxy, to become an intergalactic empire. That was always fantasy, a story we told ourselves that physics never supported. Our actual role, the only role available to us, is to be the consciousness that understands this particular galaxy, the intelligence that asks questions about this region of space, the civilization that creates meaning within these boundaries. And perhaps we're not alone in this. If Dr. Rees is right about cosmic loneliness, if every civilization everywhere faces the same limitations, then the universe might contain 2 trillion islands of intelligence, each confined to its galaxy, each creating its own meaning in isolation. That's not a universe of empires and conquest. It's a universe of introspection and depth, where intelligence turns inward and upward rather than outward. The Buddhist concept of samsara, the cycle of suffering caused by attachment and desire, teaches that liberation comes from accepting what is rather than craving what isn't. Craving intergalactic. Expansion creates suffering because it's desire for something fundamentally unavailable. Accepting galactic confinement ends that particular form of suffering and allows appreciation for what's actually present. This galaxy, these stars, this pocket of cosmos that contains us, you might find this perspective unsatisfying. Part of being human is wanting more, pushing boundaries, refusing to accept limitations. That drive has accomplished tremendous things. It's why we have civilization, technology, science. But there's a difference between boundaries we can push and boundaries that push back with the full force of physical law. Recognizing the difference isn't defeat, it's maturity. The ecologist Aldo Leopold wrote about developing a land ethic, a sense of belonging to a place rather than ownership of it. Perhaps we need a galactic ethic, a sense that we belong to the Milky Way, that our relationship with our galaxy is one of inhabitant rather than conqueror, appreciation rather than exploitation.
We're not trapped here.
We're home here. This is where we emerged, where we evolved, where we belong. The rest of the universe exists, but it exists for others, other forms of intelligence, other conscious beings, other islands of meaning in their own galactic gardens. There's something almost sacred about this limitation. The universe is saying you cannot have everything, you cannot go everywhere, you cannot know all. You must work within constraints. You must find depth rather than breadth. You must create meaning from finite materials rather than infinite possibilities. This isn't cruelty, it's the condition that makes meaning possible. Without boundaries, nothing has definition. Without limits, nothing has value. The universe has given us exactly enough space, not too little to matter, not too much to comprehend. When you look at the night sky now, you can see it differently. Those distant galaxies aren't destinations or frontiers. They're reminders. Reminders that the universe is larger than we can ever access, that reality extends beyond our reach, that existence includes vast territories we'll never visit. But they're also reminders that we have our own territory, our own galaxy, our own corner of cosmos to understand and inhabit and find beautiful. We're not excluded from the universe. We're included in exactly the portion available to us. The Milky Way contains 400 billion stars, 400 billion chances for wonder, for discovery, for worlds unlike anything we've imagined. We could explore for 1 million years and not exhaust its possibilities. We could study it for 1 billion years and still find new questions. This galaxy alone is enough, more than enough, for the entire span of human existence. We don't need more. We need to appreciate what we have. Accepting boundaries doesn't mean abandoning ambition or curiosity or the drive to explore. It means redirecting these impulses toward what's actually possible. We can still reach for nearby stars, still attempt to understand our galaxy deeply, still seek out life within our cosmic neighborhood. We can still push against every boundary that's actually pushable. But we stop wasting energy mourning boundaries that won't move. Stop resenting limitations written into the fabric of reality. Stop feeling imprisoned by constraints that simply define our context. The prison dissolves when you stop seeing it as a prison. The Milky Way is not a cage, it's a home. The boundaries are not walls, they're definitions. A confinement is not limitation, it's focus. We will never leave this galaxy, and that's exactly as it should be. This is where we belong, where we've always belonged, where we'll remain for as long as humanity exists.
And that's not tragedy.
That's home. Throughout this journey, we've discovered why the dream of intergalactic expansion must remain forever a dream, not because we lack ambition or technology will fail, but because reality itself forbids it. We've seen how the scale of space dwarfs human comprehension, how the velocity prison of light speed cannot be overcome, and how energy requirements exceed all the power our civilization will ever generate. We've confronted the temporal trap that makes meaningful journeys impossible across cosmic timescales, and the biological cage that confines consciousness to conditions found only on our home world. But perhaps the most profound insight is this: accepting our boundaries doesn't diminish us. It defines us. We are beings evolved on Earth, shaped by this specific planet's gravity and chemistry and light. We are conscious minds operating within physical bodies that need specific conditions to survive. We are temporal creatures asking eternal questions, finite beings grasping toward infinity. And all of that happens here, in this galaxy, on this timescale, within these constraints. Trying to escape what we are in order to go where we cannot means losing ourselves in the pursuit of an impossible goal. The universe has drawn a circle around the Milky Way and said, "This is yours."
All of it, completely.
100,000 light years across, containing more stars than humans who have ever lived, harboring worlds beyond counting and wonders beyond imagination. This galaxy alone could occupy humanity's curiosity and exploration for millions of years. We haven't explored 1/1,000,000th of 1% of what's available to us here, and we're already mourning what we can't access beyond. As you go about your day after watching this, remember that you're standing on a planet orbiting a star in a galaxy that represents both your home and your horizon. When you look up at the night sky, you're seeing the boundaries of all human experience. Everything humanity was, is, or ever will be, exists within this one galaxy. That's not a limitation to resent.
That's a context to appreciate. You're not trapped. You're located. You're not confined.
You're defined.
You're not excluded from the cosmos.
You're included in exactly the portion where consciousness like yours can exist. The distant galaxies we see through our telescopes aren't destinations we've been denied. They're evidence of the universe's vastness, reminders that reality extends far beyond what any one civilization can access. Other intelligences, if they exist, face the same boundaries, trapped in their galaxies as we're trapped in ours, wondering about us as we wonder about them, forever separated by distances that no technology can cross. The universe isn't designed for empires or conquest. It's structured for isolated pockets of meaning. islands of consciousness creating significance within their local territories. This is what it means to be human in a cosmos that operates on scales incompatible with human ambition. We can understand the universe through science, can observe distant structures through ever more powerful telescopes, can theorize about conditions in regions we'll never visit. But we will always be here, in the Milky Way, looking outward from our galactic home with a mixture of wonder and acceptance. We can see almost everything, but we can touch almost nothing.
And that's fine. Understanding is enough.
Knowledge is enough. Being here, in this galaxy, with these possibilities, is enough. The most profound realization about cosmic confinement is that it changes nothing about what makes life meaningful. Love, creativity, discovery, connection, beauty, understanding, growth, compassion, none of these require intergalactic access. They emerge from consciousness interacting with reality, from minds grappling with existence, from beings creating significance in the face of an indifferent universe. Whether we're confined to one planet, one solar system, one galaxy, or spread across many makes no difference to the meaning we can create and experience. You are not separate from the Milky Way, you are an expression of it. Your body is built from elements forged in stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and scattered across the galaxy by supernovas. You are literally made of the Milky Way, and you are its way of knowing itself. This galaxy created you, evolved you, gave you consciousness so that through you, the cosmos can observe and understand and wonder at its own existence. You're not an outsider looking at the galaxy. You're the galaxy looking at itself. So no, we will never leave the Milky Way. We will never visit Andromeda or the Triangulum Galaxy or any of the 2 trillion other galaxies scattered across cosmic distances. We will never meet alien civilizations from other galaxies, never see what wonders evolution created in completely foreign environments, never understand the full diversity of what consciousness can become across infinite contexts. Those possibilities exist, but they exist for others, or they exist only as abstract knowledge, patterns we can grasp through mathematics and observation, even if we can never experience them directly. But what we have, this one galaxy with its 400 billion stars, its uncounted planets, its vast territories of exploration and discovery, is not a consolation prize. It's everything we need, everything we could use, everything that can possibly matter to beings like us. The Milky Way is our home, our context, our complete cosmic environment. And accepting that doesn't mean giving up. It means focusing on what's actually possible, what's genuinely meaningful, what can truly matter within the constraints reality has given us. If you made it this far, subscribe and give a thumbs up. Check out my video on the true scale of black holes. I'm sure you'll love it. These cosmic truths reshape how we understand our place in reality, and there's so much more to explore about the boundaries that define existence itself. The universe showed us infinity while confining us to finitude. It gave us curiosity without limits while establishing boundaries we cannot cross. It taught us to dream of cosmic expansion while making that dream physically impossible. And in doing so, it taught us the most important lesson of all. Meaning comes not from accessing everything, but from deeply inhabiting something. We will never leave the Milky Way, and that's exactly how it